So in the last video we derived this algorithm which we're going to use in order to allow us to add and subtract our 32-bit floating point numbers. We said the value inside the brackets would give us the absolute value of the result, and the value outside the brackets would give us the sign. And we also mentioned that there was situations where the sign inside the brackets here was a negative. In that case we had to go through this truth table here. Now what we're interested in this video is how to actually perform the addition and subtraction. So we're going to have this part here which is really inside the brackets. So we're going to have the value for x plus or minus the value for y. Now we're going to write the number out in its floating point representation. So it's going to have a mantissa for x, it's going to have a base, which in this instance is going to be the base of 2, but throughout the video we'll use the base of 10, just because it's something that we're more used to seeing, and we'll use that as examples. And we're going to have the exponent for the value of x, we'll have the mantissa for y, the base for y, and the exponent for y. So the question is, how do we do this adding and subtracting? That's what we're going to look at in this video. So in order to work out how we're going to do this addition and subtraction, we'll make a comparison to the decimal system, and we'll look at a couple of examples here. Now let's say for example we have the number 2.35 times 10 to the 6, so that's our x value, and our y value is 7.45 times 10 to the 3. Now if we were going to add these together, we couldn't simply add the 2.35 and the 7.45. And we can see that because if we were to extend this out and just write it without the exponent, then this number would be 235 and there would be 1, 2, 3, 4 zeros. And this number here would be 7450. And in order to add these, we would have to position the 7450 at the end here. This is going to be our units, tens, hundreds and thousands. So we would position that 7450 and then the 235 and the 4 zeros. We would add them together, we would get this number here. And then we could put it back into our exponent format. And that would be our value 2.35745 times 10 to the 6. So we would just be taking our full stop here 6 places along, 1, 2, 3, 4, 5 and 6. So what we want to do is we want to make the exponents the same before we do the addition. So that means we could make the smallest exponent equal to the largest exponent, or equally we could make the largest exponent equal to the smallest exponent. So the route that we're going to do here is we're going to take the smallest exponent and we're going to increase it to the size of the largest exponent. Now whenever we do this, we're going to have to then reduce the size of the mantissa accordingly. So let's say y has the smallest exponent, which is a value of 3. So we're going to make that exponent a value of 6. So in effect we'll have increased the number by 1000. So in order to get the correct number, we're going to have to then decrease the mantissa also by a factor of 1000. So if we take the value for our y, which is 7.45 times 10 to the 3, then we're going to increase that 10 to the 3 to 10 to the 6. So that's an increase of 1000. So in order to make the number the same, we're going to have to decrease the mantissa here equally by a value of 1000, such that we've got our 7.45 times 10 to the 3, and it's going to equal 0.00745 times 10 to the 6. So that means that by making the exponents the same, we can have the exponents here at 10 to the 6, exponent is 10 to the 6. So whenever we add these two together, we're going to get our 2.35745 times 10 to the 6, which is the same as what we have above. Now you'll notice in example 1 that we had to increase the value of the exponent by 1000 and decrease the value of the mantissa by 1000. In example number 2, you'll notice that the y value actually has a larger exponent than the x value. So that would mean that if we were to realise this in an actual circuit, we would have to swap the values for our x and the y, because the circuitry that we would have access to and designed will make the exponent larger and the mantissa smaller. And in order to get the right answer, we would have to therefore ensure that we were using this value here. This would be making the exponent of x larger and the mantissa of x smaller. So what we can do in order to reuse that one piece of circuitry is just swap the values for our x and y. So that is, we want to ensure that the exponent for x is always greater than or equal to the exponent for y. Now we could do it and have two lots of circuits, and we could have a circuit that could make the exponent larger or smaller and the mantissa larger or smaller. But in order to cut down that amount of circuitry, we only need to ensure that we swap the values here, x and y, at the inputs to our circuit. So this ensures that our circuit only ever has to increase the exponent and decrease the mantissa. So it simply makes the circuit smaller and a much easier and neater design. Also notice here in the answer, the value for the exponent is going to be the largest exponent value. So in this case here, it would be 10 to the power of 6. And the largest exponent value we know is always going to be the x exponent. So we can just set the answer tentatively to the value of e to the x. So let's go to the next page and we'll summarise what we've learned here. And we'll be almost finished on with our basic algorithm. So we said we want the exponent for x to be greater than or equal to the exponent for y. And we wanted to do that in order to cut down in the complexity of our circuits. Also, the final result for the exponent is going to be given by the largest exponent, which is the exponent of x. Now that's not the end of the matter. There are circumstances where we're going to have to change this exponent value, but we'll get on to that in the next video. We're also going to have to decrease the value of the mantissa. And this is a little equation here that tells us how to decrease that. So let's say, for example, we had the number 7.45 times 10 to the 3, and we increased the exponent by 1000, so that would then go from 10 to the 3 to 10 to the 6. Then we would have to decrease this number here by 1000. So we're going to decrease this number by the difference between the two exponents. So we would do 6 minus 3, and that would give us a value of 3. But we're going to have to decrease it, so we're going to have a minus sign outside here. So in effect, in the example below, this would be beta, which in this instance would be 10 to the power of minus 3. So that would be telling us that my would be decreasing by a factor of 1000. As we mentioned above, we're going to make the exponent for the result, which we can call here ER, equal to the largest exponent, which is going to be the EX. Now we're going to have to go through either an addition or a subtraction. So we're going to have to add or subtract the mantissas. So we're going to have the mantissa for x, and then we're going to have to add or subtract. Now the add or subtract we said is going to be given by this little algorithm here, which is going to be minus 1 to the power of s z, where s z is the exclusive OR of the signs of x and y. So that tells us whether we're going to do the addition or subtraction algorithm. But we're going to do the addition or subtraction on this term here. So this is the term here, which is the mantissa, which has been decreased by the value ex minus ey. So the final result is going to be given by this value, which we can call mr, which is this value above, and it's going to be times beta to the power of er. Now er is this exponent value, and we're going to have the sign, which is going to be given by minus 1 to the power of sr. Now our sr here is going to be given by this term here, our minus 1 to the sx, and also our truth table, which we've seen on the previous page. So this is the final answer here, but we're also going to have to normalise this in certain situations, and we'll look at the normalisation phase as well over the next few videos. But this is the basic algorithm that we're interested in. But we've still got a bit more to cover in order for this to adhere to the IEEE 754 standards. We're going to have to look at subnormal numbers, we're going to have to look at special values, and we're going to have to look at rounding. But this is enough of the mathematics and enough of an algorithm to allow us to get started. So in the next video, we'll look at the example of addition in Excel VBA, and I'm hoping that by using the VBA tool that we can actually chase up the ones and zeros, and a lot of the mathematics you see here will become more understandable and more obvious to us. So thank you for listening. I'll get you on the next video. Goodbye.